Okay, this is the second part of non-uniform cylindrical charge distributions. I just needed a little more time to finish up this problem. So we were in the middle of this problem. Just to recap, we have a cylinder that the charge isn't uniformly distributed. As you go out, the charge density gets greater and greater and greater. The way you handle this is, you first, if you want to know the field, say right here, you draw a Gaussian surface that goes through that point. And then to get the charge enclosed, what you need to do, and this is tricky, is add you have to add up a bunch of charges that are in cylinders as you go out. So you find the charge enclosed in this cylinder and every other one. And so this is the cylindrical shell. So what I mean is that this charge Q shell is not the charge inside here. It's not the charge inside here. It's the charge inside here. That's the charge enclosed. It's the charge enclosed in there, not in the whole thing. And so what you're doing then is you're using that rho is equal to this, but if it's varying, you can also say it's equal to dq over dv. It's equal to the charge enclosed in the shell divided by the volume of the shell. Well, if I bring the dv over here then, come on down here for a second. So rho dv is equal to dq. So the dq in a shell, a cylindrical shell, is equal to rho times dv. Now remember that, because rho is beta r. So what I'm doing here is this is Gauss's law. The charge enclosed is rho dv, then sum up all those charges enclosed in the cylinders. So this, and I don't want to just keep summing them all the way out to the edge. I want to stop at the Gaussian surface, because this is the charge enclosed by the Gaussian surface. Okay, so what I'm going to do is I'm going to take this integral then, and let's do. I can pull out all the constants. So I have 2 pi h beta. I think I've been calling that b, but it's beta. So 2 pi h beta, and then that's going to be r squared dr from 0 to rg. And that's equal to, I'll bring the epsilon naught over on the other sides just to keep it even. Okay, let's take this integral then. That's going to be 2 pi h b beta. And then the value of this integral is going to be 1/3 r cubed from 0 to rg. Okay, I suppose we can get rid of the h and the 2 and the pi. And let me solve this then. If I put in rg, I get that's going to last, but when I put in 0, that's going to disappear. So it's just going to be beta rg cubed. What is rg? Rg is the radius of the Gaussian cylinder. So beta rg cubed over 3 is equal to E rg epsilon naught. Did I get all that right? I think that works. All right, so let's then just bring everything else over here. So we can get rid of an rg. That goes to squared. And so the electric field is beta rg squared all over 3 epsilon naught. This is the electric field inside a cylinder that has that charge distribution. So look, as you go out, it gets greater and greater. The field gets greater and greater. It's directly proportional to R squared this time. Now you might ask, what about, how would this problem be different if we went to the outside of the sphere? If I wanted to know the field there, how would I actually go about doing that? Well, it's not that bad. First of all, the field here is this way. And what you're going to do is you're going to just put in a Gaussian sphere, a cylinder rather. I hope I've been saying cylinder this whole time. There shouldn't be any spheres. Okay, my drawing's a little messy here, but there's my Gaussian sphere out here. And so this is what it would look like if you want to get the E outside there. What you do is you'd sum up all the charges enclosed by your Gaussian cylinder. And so it would be Q enclosed over epsilon naught, but Q enclosed is this. It's beta R, that's rho, times dV. Now dV is 2 pi RH dr, a length, a width, and a length, a height, and a width. This is the volume of a shell, which is the volume of the shell. But we're going to ask it to go, now we want the calculus to say add up only from 0 to capital R. Don't keep adding as you go out. See, the math doesn't know that the charge stops right here. So you have to tell it, like when it adds, don't go all the way out to this R. Stop at the capital R. Okay, so that's the charge enclosed. That's the total charge enclosed. I'm going to bracket that just to make it neater. That's all divided by epsilon naught. And that should equal, now you can make all the arguments again for Gauss's law, like dA, here's the direction of dA, it's radially outward. And so the E and the dA are always in the same direction. There's no flux out the top and bottom. And so we're left with just E times dA. And why would we think why is E any stronger here than here than here than here? It's not. So you can pull that out to the integral. And when you pull that out and add up all the dAs, you get this. And so there you have it. If you solve for this, you will get the E enclosed, or the E at this point. Okay. So that's not that hard of an integral. I know that looks awful, but it's very doable. All right, that's all I have to tell you. There's a lot. Okay.